the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, which is dedicated to linear algebra students who are currently going through a topic called linear independence, we're going to explore the linear independence of matrix columns. I actually used this concept in the previous video, which is titled Linear Independence and Linear Dependence. And I did so because, well, to be honest with you, it's incredibly easy to see why this is true, and we justified it pretty darn well. But let's go ahead and actually state it as a theorem, so from this point forward, we can feel confident using that idea. So here's the theorem. The columns of a matrix A are linearly independent if and only if the equation AX equals 0 has only the trivial solution. Now, in the previous video, we talked about a set of vectors being linearly independent or linearly dependent. They were linearly independent if the only solution to this vector equation is 0, the trivial solution. And that goes along with what we're stating here. If the matrix equation only has the trivial solution, and when I say the matrix equation, I mean the homogeneous matrix equation only has a trivial solution, then the columns of that matrix must be linearly independent. And the other way around, if the columns of that matrix are linearly independent, then it's only truth that the homogeneous equation AX equals 0 must only have the trivial solution by definition. So let's go ahead and actually prove it now rigorously. I'm going to use a highlighter here so that I can very distinctly identify my statements P and Q. And if you don't know what I'm doing here, this is from one of my previous videos, that when you have a theorem, an if-then statement, it is usually written as if P, then Q, or in other words, symbolically. And if your statement, as it is in this case, is a bijection, then symbolically, it is written as P if and only if Q. And when you go to prove a statement like this, you have to prove both directions. P implies Q and Q implies P. So let's go ahead and start with the forward direction here. And this shouldn't be too bad. So let A be the m by n matrix, defined as follows. A is just a matrix of column vectors. The vectors are v sub 1, v sub 2, all the way through to v sub n, where each of those vectors is in Rm. In other words, each of those vectors has m entries. That is, A has m rows, and there are n of those vectors, so it is an m by n matrix. Now we start with the statement P. We're going to suppose the columns of A are linearly independent. Well then, by definition, any linear combination of the column vectors of A set to equal 0 only has the trivial solution. That is, by definition, x sub 1 v sub 1 plus x sub 2 v sub 2 all the way up to adding x sub n v sub n equaling 0, that vector equation only has the trivial solution. But we know from matrix vector multiplication that this linear combination of the vectors v with weights x1, x2, all the way through xn can be written as follows, as ax equals 0. And since ax equals 0 is the same thing as this guy right here, and that vector equation only has a trivial solution, then the matrix equation ax equals 0 only has the trivial solution. So we have proven that P implies Q, that the columns of A being linearly independent implies the equation ax equals 0 only has the trivial solution. Now let's go ahead and prove the reverse direction. And to be honest with you, the backwards statement here is really similar to the forwards statement. In fact, we could have probably just done the forward statement as an if and only if itself, but let's go ahead and just do the backward statement as a proof here. So let's assume that Q is true. That is, we're going to assume that AX equals 0 only has the trivial solution. Since we've already stated in our proof early on the structure of A, we'll go ahead and use that in this part of the proof. The structure we're actually stealing, or not stealing, but using from earlier is the fact that the matrix A can be written as a matrix of column vectors v1 through vn. We know from matrix vector multiplication that that will be a linear combination of the columns of A itself. That's this row right here. And if we set that equal to 0, we have been told the only solution to that equation will be the trivial solution. Thus, AX equaling 0 only having the trivial solution implies that the vector equation x sub 1 v sub 1 plus x sub 2 v sub 2 all the way to the end x sub n v sub n equaling 0 only has a trivial solution, and by definition that means those vectors v1 through vn are linearly independent. And I want to talk about the language right here. If I didn't write it as a set, this is just a minor quibble, don't worry too much about it, but if I didn't write it as a set and I said, hey, those vectors are linearly independent, I would say those vectors are linearly independent. But when I'm writing as a set of vectors, I would say that set of vectors or that group of vectors is linearly independent. It's just a minor language issue. Don't worry too much about it. Some people might say, oh, you should have R there, not is or is not R. Don't worry too much about that. When you're talking about a single set of objects, it is either linearly independent or linearly dependent. When you talk about a list of items like, oh, I have this vector, that vector, that vector, and that other vector, they either are linearly independent or are linearly dependent. Anyway, not a biggie. Don't worry too much about that. Now that we know that that set is linearly independent, that means the columns of A must be linearly independent because that's what that set is. It's a set of the column vectors of A. And that's it. We have literally arrived at the statement P. We have started by assuming Q that the equation AX equals 0 only has a trivial solution. Remember, a little bit of old theory. The homogeneous equation always has at least one solution, the trivial solution. It will always have the trivial solution. But what we're saying is if it only has the trivial solution, then we've just proven that the columns of A must be linearly independent. And that completes both sides of that proof. We are done. QED. Quod erat demonstratum. So it has been demonstrated. A little aside here that I didn't bother typing out, but something that might be helpful in the future. If you're watching through all of the videos that I produce for linear algebra, then you've heard my conversation about a theorem and its contrapositive, that they are actually the same statements. So if P then Q is the same as saying if not Q, then not P. And with bijections, which are if and only ifs, the contrapositive looks like this. Essentially, it's the negation of everything. So right now we had P is true if and only if Q is true, P being that the columns of A are linearly independent, Q being that the equation AX equals 0 only has a trivial solution. But this theorem can also be stated as follows. The columns of a matrix A are linearly dependent if and only if the equation AX equals 0 has a non-trivial solution. It could actually have an infinite number of non-trivial solutions, but as long as it gets to at least one non-trivial solution, we know the columns are linearly dependent. Notice how I did that negation. The opposite of being linearly independent is linearly dependent. The opposite of saying AX equals 0 only has a trivial solution is AX equals 0 has at least one non-trivial solution. So this is another showcasing of the fact that every theorem is a 2-for-1. The theorem itself and its contrapositive. All right, now that I've said that, let's go ahead and step forward to a little bit of advice. And it's kind of unfortunate how I label my advice. I call it a how-to, and I really hate recipes in mathematics or how-tos in mathematics normally. But sometimes, just for advice or tactics, it's nice to write these down. So how-to: if you're given a set of vectors, determine whether or not they are linearly independent. So anytime you need to study the linear independence of a set of vectors in Rn, you can do so using any of the following methods. Some restrictions apply, and we'll talk about those in a moment. So the first thing that I generally do is I just form a matrix with the given vectors as columns, and then I determine if the matrix equation Ax equals 0, the homogeneous matrix equation Ax equals 0, only has a trivial solution. That's pretty straightforward and legit. That's the way to go. If you can set up that augmented system, do some row reduction, and find out that only the trivial solution exists for that homogeneous equation, the columns are linearly independent, and therefore those vectors are linearly independent. If, on the other hand, you set up that matrix, that augmented matrix for this homogeneous system, and you go to solve it, and you have a non-pivot column in the coefficient matrix, that is, you have a free variable, then you'll have an infinite number of solutions. And thus, that system has more than just the trivial solution. And hence, the columns are linearly dependent. And therefore, the given vectors are linearly dependent. That tactic is basically the one you're going to use the vast majority of the time that you're asked about linear independence or dependence of a set of vectors. However, there are some special cases. For example, check for linear independence by inspection. If one vector is a multiple of the other, the set is linearly dependent. Now, this will be a theorem later on, but it is actually a great way to check if it's super simple. So I'm going to show you an example of that. And trust me, this is not a proof that this statement is true, but it is actually true, and we'll go through later on and see it as a theorem. But I'm telling you just by inspection right now that this set of vectors is linearly dependent. Why? Because I could take 1 times vector 1 plus 0 times vector 2 and add that to 1 times vector 3. And because vector 1 and vector 3 are multiples of each other, and I've chosen the right multiple of them to offset each other, that summation is actually the 0 vector. You can try it out, add it up yourself. I promise it is. Now again, that's not a proof, that's just an example, but later on comes the proof. But to be very honest with you, that second method, checking for linear independence by inspection, is really often difficult to do. You only use that tactic if it's blatantly obvious. It is also true, actually, that if your set contains a vector that can be generated using a linear combination of another 2 vectors in your set, or 2 or more vectors in your set, it is linearly dependent as well. So this set of vectors is actually linearly dependent. Why? Because if I take one of these v1s plus one of these v2s and I subtract off one of these v3s, I promise you that will be 0. And that is because the third vector is actually the sum of the first 2 vectors. So whenever you have a vector in a set of other vectors, and if that vector is a linear combination of the other vectors in that set, then that entire set is broken. It is linearly dependent. And I say it's broken because that's how I view linear dependence. You don't want linear dependence if there's any way to avoid it. Essentially what linear dependence, in my opinion, is like, it's like if somebody is telling you the same story they've told you in the past, but just in a different way. Somebody comes along and says, I've got this story to tell. Somebody has a completely different story to tell. And then a third person comes in the room and basically summarizes those 2 stories and says that it's their story. No, it's not. That's not an original vector, and it's not an original story either. All right, let's take a look at what else we have. The third one is really interesting. A set that contains too many vectors. So I'm not going to read the rest of that yet. I will just go ahead and show you by example why a set with too many vectors is likely to be linearly dependent. And by the way, I went ahead and wrote that those two are linearly dependent. So far, this set of two vectors, so far, is actually linearly independent. I'm not going to tell you why yet, but they totally are linearly independent. But once I add a third vector in here, the set will become linearly dependent. And it has something to do with the dimension or the size of these vectors. Because these vectors only have 2 entries each, and this will be a theorem that we'll have in the future, but because those vectors only have 2 entries each, once you get to a third vector in a set, you're guaranteed linear dependence. That third vector has to somehow be a linear combination of those other 2 vectors. Let's call these vectors v1, v2, and v3. If you notice, v1 minus 2v2, that's actually equal to v3. In other words, v3 is a linear combination of v1 and v2. You can check it out, do the mathematics. I promise you that is actually true. And you say, well, what's the big deal about that? I say, well, subtract v sub 3 from both sides. And you should see the issue. There's a linear combination of these 3 vectors that will become 0, and the weights in front of all those vectors are not all 0. In fact, none of them are 0. And therefore, these vectors must be, by definition, linearly dependent. So now I'll go back to the number 3 in this list and just say it again. A set that contains too many vectors, that is, more vectors than the entries in the vectors, is always linearly dependent. So our vector set down here contained vectors with only 2 entries, and we ended up having 3 vectors. Once you get to more vectors than those vectors have entries, the set is linearly dependent. Again, that will be a theorem we'll see in the future. And a little note on this, if represented as matrix columns, these are quickly recognizable as short and wide matrices. So something like this. That is a short and wide matrix. Every vector only has 3 entries, and yet I have 6 vectors. So I can guarantee the columns of that matrix are linearly dependent. Just letting you know that you can't actually use that yet because we have not proven it, but that is a result we will arrive at via a proof. And once we do, you're more than welcome to use it. Finally, any set containing the 0 vector is linearly dependent. That one's really a rarity, but it's still very important theoretically because it does come up in theorems. So why is it that any set containing the 0 vector is linearly dependent? Well, let's suppose that we have the set, I'll just throw the 0 vector at the beginning, 0, 0, 0, 1, 0, 0, and let's do 0, 1, 0. Each vector only has 3 entries. We have 3 vectors. So we're not going to break the world by having only 3 vectors here. It could be that this set is linearly independent until you realize that last little statement, which is that any set containing the 0 vector is linearly dependent. Well, let's figure out why. For a set of vectors to be linearly dependent, we need to find one or possibly more, but generally we just need one set of coefficients or weights, C1, C2, and C3, where not all of those weights are 0, such that the linear combination of the vectors using those weights turns into 0. That is, I need the sum of these vectors to turn into 0 without all their coefficients being 0. Well, here's one such linear combination. Notice not all of the weights are zeros. One of them isn't. So that is a linear combination of those vectors, and by the way, that does become 0 because v sub 1 is the 0 vector, so pi times v sub 1 is still 0. The rest of them are 0, and so all that sums up to the 0 vector. So there you go. Those are 4 kind of tactics that you would use. The last 3 are happenstance. You kind of use them on occasion, but rarely. You're rarely going to get a set containing the 0 vector because it's very quickly obvious that it's linearly dependent. And it's really hard to check for linear independence by inspection. Generally, you have to resort to forming a matrix, step 1 there. However, the third one does come up every once in a while, where you just have a short but wide matrix. You know immediately the columns of that matrix are linearly dependent because you have more vectors than they have size, or entries, if you will. All right, all that being said, here we go. Determine if the columns of the matrix are linearly independent. Or I could have worded it differently and said, determine if the columns of the matrix are linearly dependent. It doesn't really matter. You're doing the same action no matter what. So the very first one, I will go quickly looking at the columns and seeing if one is a multiple of the other. And if I look at that, I can't really see quickly that column 2 or column 3 is a multiple of the previous columns. So I probably won't bother with that. Each of those vectors has 3 entries and there are 3 vectors, so I'm not breaking the law there. So the only way that I'm going to do this is form an augmented matrix and do some row reduction. Now, remember, I had given some advice in the previous video that when you solve AX equals 0, some people have a habit of not writing that 0 column, the augmentation column, but it's actually a bad habit because you tend to forget what you're dealing with. You might be working with an augmentation column or not. It's better to write one in there. It doesn't cost you a lot. So let's just do it. And again, you could see this is a augmented matrix that we've seen several times in this course already. Let me just showcase it. Most recently, we saw it in this example right here, example 1.7, number 1. Here's the augmented matrix we've been handed, 1, 2, 3, 4, 5, 6, 6, 7, 8. And it row reduces down to this right here, which I'll copy over, and we get this right here. We see we have a pivot in the first column, a pivot in the second column, but no pivot in the third column. Now remember, AX equals 0 always is consistent. So if we are looking at, which we are, the matrix equation AX equals 0, we know there's at least one solution. So I know this is not going to be an inconsistent system, for example. So I don't have to worry about a pivot in the rightmost column. That's basically what I'm saying. But we do have a non-pivot column in the coefficient matrix, which tells us that the corresponding system has an infinite number of solutions. So a non-pivot column in the coefficient matrix implies the corresponding system has an infinite number of solutions. Our system is AX equals 0. So that means, since we have an infinite number of solutions, we must have a non-trivial solution. And by the previous theorem, if AX equals 0 has a non-trivial solution, the columns of A are linearly dependent. Now, because we have used that example over and over again, it's probably nice to do a different example. So let's play with this guy right here. Place this in an augmented matrix and go ahead and do row reduction techniques. Now that we have this right here, you can see we have a pivot in every single column of the coefficient matrix, which means we don't have any free variables. And remember, AX equals 0 is always consistent. So if there are no free variables, that means the solution is going to be unique. And if the solution's unique, meaning there's only one solution, it must be the trivial solution, because again, homogeneous equations always have the trivial solution. And that implies the columns of the matrix A are linearly independent. So you can see we're kind of revisiting all the old stuff that we learned back in earlier in this course when you're doing row reduction techniques. That's why row reduction techniques, reduced row echelon forms, all that stuff. It's very important early on because you're using that nonstop in linear algebra. And that's also why, by the way, some people teach this course as if it's just a computational course, and it's not. Anyhow, I hope that this video helps you out in some way, shape, or form. Stay tuned for my videos in the future, and I hope to see you there. Have a great day. Be wonderful human beings.
It's the system of equations we must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.